A silent war is raging across the cosmos, and its outcome will decide the fate of everything. This conflict pits the familiar pull of gravity against a mysterious repulsive force known as dark energy. Modern science has made a startling discovery. The expansion of our universe is not slowing down as expected. It is accelerating, defying our most fundamental laws of physics. This video will guide you through the hidden architecture of dark energy, from its theoretical roots to the advanced telescopes hunting for its signature. You will gain a clear understanding of one of the greatest scientific mysteries of our age. We will explore whether the cosmos is destined for an eternal freeze or a violent rip. Could our entire understanding of gravity be wrong? Gravity has always been the universe's great architect, the invisible hand sculpting galaxies and pulling stars together from primordial chaos. Yet for most of human history, we believed its influence was absolute, that its relentless pull would one day reign in the entire cosmos. This long-held assumption was shattered in the late 1990s. Two independent teams of astronomers were studying distant stellar explosions known as Type 1, a supernova. These cosmic beacons have a known intrinsic brightness, allowing scientists to gauge their distance with remarkable precision. By measuring how much the light from these explosions had stretched or redshifted, they could also determine how fast the universe was expanding when that light began its journey billions of years ago. The data delivered a result so bizarre that scientists initially doubted their own work. The distant supernovae were fainter than expected, meaning they were farther away. This could only mean one incredible thing. The expansion of the universe is not slowing down under gravity's pull. It is speeding up. Some mysterious repulsive force, working against gravity on the largest scales, was shoving galaxies apart at an ever-increasing rate. This discovery of an accelerating universe was a profound paradigm shift, a cosmic revolution that earned its discoverers the Nobel Prize. It forced a dramatic rewrite of the universe's energy budget, introducing a dominant new component we now call dark energy. The cosmic stage was instantly transformed. We went from a universe destined for a slow, gravitational collapse to one careening toward an unknown fate, a grand conflict between the inward pull of everything we can see and touch and the outward push of a force we cannot see at all. This is the fundamental drama that will decide everything. Will the relentless push of dark energy ultimately tear every atom apart in a big rip? Or will it lead to a slow, cold fade into a big freeze? The answer lies in the hidden nature of this mysterious dominant force. We feel its pull every single day, the gentle, constant force that keeps our world from flying apart. This is gravity, the universe's great architect. For centuries, we understood it as a simple attractive force. But Albert Einstein gave us a far more profound and beautiful picture. He proposed that space and time are woven together into a single fabric called space-time. Think of a taut rubber sheet. When you place a heavy object like a bowling ball in its center, the sheet stretches and warps. Now roll a marble near this depression. The marble will spiral inward, not because of some mysterious force, but because it is following the curved path created by the bowling ball's weight. This is the essence of general relativity. Mass and energy tell space-time how to curve, and that curvature tells matter how to move. The sun's immense mass creates a deep well in the cosmic fabric, and Earth, like that marble, simply follows the curved path, trapped in an eternal orbit. This is the gravitational glue that built our cosmos. It pulled sparse clouds of primordial gas into the first stars. It gathered those stars into magnificent galaxies, and it bound galaxies together into vast clusters that stretch across millions of light years. All the structure we see, the great cosmic web of filaments and voids, is the masterpiece of gravity's relentless, patient, attractive work. For so long, this seemed to be the universe's only story, a slow, grand gathering. The shocking discovery of cosmic acceleration revealed a stunning truth. This master architect, for all its power, has a silent, dominant rival. But this elegant picture of a cosmos governed solely by gravity held a fatal flaw, one revealed by staring into the deepest reaches of space. The story of its undoing begins with a particular kind of stellar explosion, a cosmic bomb of such predictable power that astronomers use it as a universal measuring tape. These are Type 1, a supernova, the violent deaths of dense stellar remnants. Because they all explode with nearly the same intrinsic brightness, scientists can calculate their true distance by observing how dim they appear from Earth. It is like knowing the exact wattage of a light bulb. A fainter bulb must be farther away. In the late 1990s, two rival teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, were using these cosmic light bulbs to measure the universe's expansion history. They expected to see the distant, ancient supernova appearing relatively bright, evidence that the young universe was expanding rapidly before gravity began to put on the brakes. Instead, they found the opposite. The most distant stellar explosions were significantly fainter than their models predicted. This meant they were much, much farther away than anyone had thought possible. There was only one logical, yet utterly shocking explanation. The expansion of the universe was not slowing down at all. It was speeding up. Imagine gently tossing a ball into the air, expecting it to slow, stop, and fall back to you. But instead, the ball shoots upward faster and faster, defying gravity itself. This was the monumental reality the data presented. The teams, skeptical of their own results, checked and rechecked for errors. They considered interstellar dust, evolutionary changes in the stars, every conceivable alternative, but the evidence was unequivocal. In 1998, they announced their findings to the world, a discovery that would later earn them the Nobel Prize. The universe was being pushed apart by a mysterious, repulsive force. This was not a small correction to our cosmic model. It was a fundamental rewrite of reality. The most familiar force in the cosmos, gravity, was not the final word on its fate. A new, dominant player had entered the arena, one that worked in direct opposition to gravity on the grandest scales. Scientists were forced to confront a simple, staggering question. What invisible hand is doing this? That mysterious force needed a name, and so dark energy was born. Yet its most compelling explanation was not a new idea at all. It was a ghost from the past, a concept its own creator had tried to erase. The story takes us back to 1917, to the mind of Albert Einstein himself. He had just unveiled his monumental theory of general relativity, a new description of gravity that portrayed the cosmos as a dynamic, evolving entity. But Einstein, like nearly all scientists of his time, believed the universe was eternal and static, neither expanding nor contracting. His own equations, however, told a different story. They predicted that a universe filled with matter should be unstable, either collapsing inward under gravity or flying apart. To force his theory into alignment with the static model he believed in, Einstein introduced a fudge factor, a mathematical term he called the cosmological constant, represented by the Greek letter lambda. This constant was a sort of anti-gravity, a repulsive energy woven into the very fabric of space itself, designed to perfectly balance the inward pull of matter and hold the cosmos in a steady state. Then, just over a decade later, Edwin Hubble made his landmark observation. By studying the redshift of light from distant galaxies, Hubble proved the universe was not static at all. It was expanding. Einstein had missed one of the greatest predictions of his own theory. Upon hearing the news, he reportedly declared the cosmological constant his greatest blunder and removed it from his equations. For decades, lambda was a forgotten footnote, a symbol of a brilliant mind's error. But the discovery of the accelerating universe in 1998 changed everything. The cosmological constant was resurrected from the dustbin of scientific history. It turns out Einstein's blunder was not the idea itself, but his reason for introducing it. He added lambda to make the universe stand still, when in reality, it was the very thing needed to make the universe fly apart. So what exactly is this cosmological constant? In modern terms, it represents a constant energy density inherent to the vacuum of empty space. Think of the void not as truly empty, but as a seething sea of quantum activity, where virtual particles flicker in and out of existence. This quantum froth imbues every cubic centimeter of the cosmos with a tiny, unchanging energy. On the scale of a human or a planet, this energy is negligible. But when you add up its effect across the vast, expanding volume of the universe, it becomes overwhelmingly dominant. And according to general relativity, this type of energy, this pressure of the vacuum, generates a repulsive gravitational effect. It is a breathtaking irony. The same theory that gave us our deepest understanding of gravity's attractive nature also contains the mathematical seed for its greatest opponent. The cosmological constant fits the data for dark energy almost perfectly, providing the constant, gentle push that accelerates the cosmic expansion. This story is a profound lesson in science. An idea discarded as a mistake can lie dormant for generations, only to be triumphantly reclaimed when new evidence sheds a different light. The question now is whether this elegant solution is the final answer, or if the true nature of dark energy is even stranger. Yet Einstein's cosmological constant is not the only possible explanation. What if the force driving cosmic acceleration is not a steady, unchanging presence, but something that ebbs and flows, a dynamic entity with its own history and future? This idea is known as quintessence, named for the fifth element of ancient philosophy, the substance of the heavenly bodies. Quintessence proposes that dark energy is a field that permeates all of space, a cosmic fluid whose properties can change over time. Unlike the static vacuum energy of the cosmological constant, quintessence is a dynamic scalar field, meaning its energy density can slowly decrease, increase, or even oscillate as the universe evolves. This single distinction opens up a breathtaking range of possible futures. If the repulsive pressure of this field weakens over time, gravity could eventually regain the upper hand, potentially leading to a cosmic recollapse. If the field strengthens, the acceleration could become far more violent than we see today. The most extreme version of this is the terrifying scenario known as the Big Rip. In this future, the repulsive force of dark energy grows without bound, becoming so overwhelmingly powerful that it overwhelms every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies, the gravitational bonds within our own Milky Way would snap. As the end approaches, stars would be ripped from their planetary systems. Finally, in the last moments, planets, atoms, and even the very nuclei of atoms would be shredded into their most fundamental components. The universe would end not with a slow fade, but with a catastrophic, instantaneous disintegration of spacetime itself. This is the profound implication of a dynamic dark energy. The simple question of whether dark energy is constant or changing is the difference between a predictable, cold future and one of unimaginable cosmic violence. This is why the search for quintessence is so urgent. Astronomers are building ever more powerful telescopes and conducting vast sky surveys, not just to map the cosmos, but to measure the history of its expansion with exquisite precision. They are looking for the faintest whisper in the data, a subtle sign that the push of dark energy was slightly different in the ancient past than it is today. Finding that tiny signal would reveal that the hidden architecture of our universe is far more complex and alive than we ever dreamed. So this quantum sea, this energy of empty space, seems like the perfect candidate for dark energy. But here we encounter one of the most baffling contradictions in all of modern science, a problem so severe it keeps physicists awake at night. It is called the cosmological constant problem. When we use our most successful theory of the small quantum field theory to calculate the energy that these flickering virtual particles should contribute, we get a number. It is a number of such staggering magnitude it is almost impossible to comprehend. The theoretical prediction suggests that the vacuum should be brimming with so much repulsive energy that it would have torn the universe apart in its first moments of existence. Not just a little bit, but instantly, the calculated energy is 10 to the power of 120 times greater than the gentle acceleration we actually observe. To put that number in perspective, it is more than a trillion times the difference in scale between the entire observable universe and a single, solitary proton. It is the worst theoretical prediction in the entire history of physics. This is not a small rounding error. It is a chasm of misunderstanding so vast it suggests we are missing something fundamental about the nature of reality itself. How can the energy we calculate be so unimaginably enormous, while the energy we measure is so subtle and slight? This discrepancy forces us to confront a humbling possibility. Either our theories of the quantum world are profoundly incomplete, or some unknown, exquisite cancellation mechanism is at work, fine-tuning the universe with a precision that defies all chance. This is the hidden architecture of dark energy, a foundation built upon a mystery within a paradox. The very fabric of empty space holds a secret, and unlocking it may require a revolution in physics as great as the one that gave us relativity and quantum mechanics in the first place. This cosmic struggle between the push and the pull is not hidden. Its evidence is written across the heavens in the grandest possible handwriting. To see it, we must pull back from individual galaxies and view the cosmos on a scale so vast it defies human intuition. We find ourselves living within an immense cosmic web, a delicate, frothy structure spanning billions of light years. Picture a sponge, but one where the solid filaments are made of galaxies and the vast, empty bubbles are unimaginably huge voids. This is the large-scale structure of our universe, and it is the primary battlefield where dark energy and gravity wage their silent war. Gravity is the great builder of this web. In the early universe, tiny, random ripples in density, imperfections in the primordial soup served as seeds. Over billions of years, gravity relentlessly amplified these tiny flaws. It pulled matter from the emptier regions into the slightly denser ones, weaving the sparse gas and dark matter into great walls and filaments of galaxies. The majestic clusters where thousands of galaxies swarm together are gravity's masterpieces, the nodes where the web's threads meet. For eons, this was the only story, a slow, patient construction project on a cosmic scale. But dark energy is the great suppressor. As the universe expands, this mysterious force exerts a counterpressure. It does not destroy the web that gravity built, but it acts as a cosmic drag, making it increasingly difficult for gravity to pull new material into these structures. Imagine trying to build a sandcastle while standing on a sheet of ice that is constantly accelerating away from you. Each new handful of sand becomes harder to reach and harder to place. This is the effect dark energy has on the growth of cosmic structure. On the scale of a single galaxy cluster, gravity still reigns supreme. But on the very largest scales, across the immense voids and the faintest tendrils of the web, dark energy's repulsive push is actively working to halt the construction, freezing the universe's large-scale architecture in its current form. We can raid this battlefield report through monumental projects like the Sloan Digital Sky Survey. This ambitious endeavor has meticulously mapped the positions of millions of galaxies, creating a three-dimensional atlas of the nearby universe. By analyzing this map, scientists can measure the precise statistics of the cosmic web, how clustered the galaxies are, and the sizes of the vast, empty voids. This distribution is a fossil record, encoding the entire history of the struggle. It tells us when dark energy began to dominate the cosmic energy budget, and how strongly it has been opposing gravity's pull. The subtle patterns in this galactic cartography are the key to understanding the rules of this cosmic conflict and ultimately predicting its final outcome. Buried within the grand cosmic web is a fossilized echo, a pattern set in stone when the universe was a mere infant. This echo provides a yardstick of almost unimaginable precision, a standard ruler we can use to measure the expansion of space itself. It is called Baryon acoustic oscillations. To understand this, we must journey back to the universe's first 400,000 years, a time when it was a seething, opaque plasma, so dense that light could not travel freely. In this hot primordial soup, matter was locked in a constant tug of war. The intense pressure of photons, the particles of light, was trying to push ordinary matter, or baryons, outward, while gravity was relentlessly trying to pull it all back in. This created a series of pressure waves that rippled through the plasma, much like sound waves moving through air. These were literal sound waves crossing the infant cosmos. Then, in a single, transformative moment, the universe cooled enough for atoms to form. Suddenly, light could travel unimpeded, and matter, no longer buffeted by that intense radiation, froze in place. The traveling pressure waves stopped dead in their tracks. Imagine a circular wave spreading across a pond that instantly turns to solid ice, preserving the exact size of the ripple forever. This is what happened on a cosmic scale. That frozen ripple, that preferred distance where matter tended to clump, became permanently imprinted on the distribution of galaxies. Billions of years later, this pattern is still visible. When we create three-dimensional maps of millions of galaxies, we do not see a random scatter. We find a subtle, statistical preference for pairs of galaxies to be separated by a specific distance, about 500 million light-years apart. This is the BAO standard ruler. Its true size is fixed by the physics of the early universe, a known quantity. By observing this ruler at different distances, and thus different epochs in cosmic history, we can perform a remarkable measurement. When we look at a very distant, ancient part of the universe, we see this ruler at its native size. But when we measure the same ruler in the closer, more recent universe, it appears stretched. Not because the ruler itself grew, but because the space between the galaxies has expanded, making the apparent size of the ruler larger. This stretching is a direct geometric measure of how much the universe has expanded over that time span. Projects like the Dark Energy Survey use this cosmic yardstick with breathtaking accuracy. By measuring the apparent size of the BAO ruler at multiple points in cosmic history, they can reconstruct the expansion story of the universe with phenomenal precision, tracking exactly when the acceleration began and how it has changed. This provides a powerful, independent confirmation of the story told by the supernova, solidifying the case for dark energy from a completely different angle. It is a direct measurement of the hidden architecture of space-time, a geometry that reveals the invisible force warping our cosmic destiny. Measuring the cosmos demands a tool of extraordinary precision, a methodical chain of observations where each step reinforces the next. This is the cosmic distance ladder, a carefully constructed sequence of techniques that allows us to reach across the void and determine how far away celestial objects truly are. Without it, the discovery of dark energy would have been impossible. The entire endeavor begins close to home with a principle as simple as holding a finger in front of your face. Close one eye, then the other, and watch your finger appear to jump back and forth against the background. This is parallax in action. Astronomers apply this same concept by observing a nearby star from opposite sides of Earth's orbit around the Sun. They measure the tiny, almost imperceptible shift in the star's position against the fixed backdrop of more distant stars. This stellar parallax gives us a direct, geometric measurement of distance for stars within a few thousand light-years, forming the solid, foundational rung of our cosmic ladder. But to reach farther, we need a brighter, more powerful kind of beacon. This is where Cepheid variable stars enter the story. These are special stars that rhythmically pulsate, growing brighter and dimmer with a clockwork regularity. In the early 1900s, astronomer Henrietta Leavitt made a crucial discovery. She found that the true intrinsic brightness of a Cepheid is directly tied to its pulsation period. A Cepheid that takes a long time to pulse is inherently very bright, while one that pulses quickly is fainter. This period luminosity relationship was a monumental breakthrough. It meant that by simply measuring how long it took a Cepheid to brighten and fade, astronomers could determine its true wattage. By comparing this known intrinsic brightness to how dim it appears from Earth, they could calculate its distance with remarkable accuracy. Cepheids became the first true standard candles, allowing us to measure distances to nearby galaxies. They provided the critical second rung on the ladder, calibrating our next step into the true depths of space. For the vast intergalactic distances where even Cepheids fade from view, we need the universe's most powerful explosions. We return to the Type 1, a supernova, the same cosmic bombs that revealed the accelerating universe. These stellar explosions occur when a white dwarf star accumulates too much mass from a companion and crosses a critical threshold. The result is a thermonuclear detonation of such consistent power that every Type 1 supernova peaks at nearly the same intrinsic brightness. They are the ultimate standard candle, visible across billions of light-years. This is where the ladder locks into place. We use Cepheid variable stars to carefully measure the distance to galaxies that have recently hosted a Type 1 supernova. This directly calibrates the supernova's peak brightness. Once calibrated, any Type 1 supernova observed in a far more distant galaxy becomes a precise distance marker. By connecting parallax to Cepheids and Cepheids to supernova, we construct a reliable chain of measurement that stretches from our galactic neighborhood to the edge of the observable universe. The accuracy of every single rung is paramount because a tiny error at the first step magnifies into a massive miscalculation at the last. This entire meticulous process allows us to determine the Hubble constant, the present-day rate of the universe's expansion, and to trace how that expansion rate has changed over billions of years. It is this precise historical record, written in the faded light of ancient stars and explosions, that provided the undeniable evidence for a cosmos being pushed apart by an unseen hand. The cosmic distance ladder is more than a tool. It is the very foundation upon which our understanding of dark energy securely rests. This single number, denoted by the simple letter W, is the universe's most important equation of state. It is the key that cosmologists use to quantify the very nature of dark energy's repulsive push. In its most basic form, this parameter is a ratio, the pressure of dark energy divided by its energy density. For the simplest explanation, Einstein's cosmological constant, this ratio is precisely -1. Think of it as a perfect, unchanging tension woven into the fabric of the vacuum itself, a steady pressure that never varies. But what if dark energy is not so simple? This is where the equation of state becomes a powerful diagnostic tool. If dark energy is something more dynamic, like a quintessence field, then the value of W could be different from -1. More importantly, it could change over the eons, telling a story of evolution. A value slightly greater than -1 might indicate a force that is slowly weakening, potentially allowing gravity to one day stage a comeback. But the most terrifying possibility lies in the other direction. If measurements ever show that W is less than -1, we would be facing a substance known as phantom energy. This is not just a gentle, constant push. Phantom energy possesses a truly bizarre property. Its energy density would actually increase as the universe expands. This creates a runaway feedback loop of repulsion. The more the universe grows, the stronger the dark energy becomes, and the stronger it becomes, the faster it forces the universe to grow. This is the precise recipe for the Big Rip, that catastrophic endgame where every structure, from galaxies to atoms, is torn to shreds. The monumental effort to measure W with ever greater precision is therefore not just an academic exercise. It is a direct investigation into the ultimate fate of all reality. By observing the expansion history across billions of years, projects like the Dark Energy Survey and the future Nancy Grace Roman Space Telescope are essentially taking the universe's vital signs, searching for the faintest tremor in the data that would reveal a deviation from -1. That single, elusive number is the final arbiter in the cosmic conflict, the secret code that describes the hidden architecture of the void. A new eye on the cosmos is preparing to open, one designed to stare directly into the heart of this mystery. The Nancy Grace Roman Space Telescope, set to launch in the next few years, is not just another observatory. It is a machine built for a single, profound purpose: to conduct a forensic investigation of dark energy itself. Its mission is a grand synthesis, employing three powerful and independent methods to corner the truth. First, it will perform an immense survey of the sky, measuring the subtle distortions of light from billions of galaxies. This phenomenon, known as weak gravitational lensing, occurs when the gravity of dark matter, the invisible scaffolding of the cosmos, bends the paths of light rays traveling toward us. By meticulously mapping this cosmic warping, Roman will create the most detailed chart of dark matter ever made, revealing how its distribution has been influenced and suppressed by dark energy's repulsive push over billions of years. At the same time, the telescope will act as a vigilant sentinel, discovering and monitoring thousands of Type 1, a supernova, across vast cosmic distances. Each of these stellar explosions is a precise marker, and by collecting them in such enormous numbers, Roman will trace the history of the universe's expansion with a level of detail that makes our current data look like a rough sketch. It will see exactly how the acceleration has changed over time, providing a direct readout of dark energy's strength throughout cosmic history. Finally, the telescope will undertake a monumental census, measuring the redshifts of millions of galaxies to map the large-scale structure of the universe in 3 dimensions. Within this immense cosmic web, it will pinpoint the signature of Baryon acoustic oscillations, that fossilized sound wave from the dawn of time, using it as a fixed ruler to measure cosmic distances with phenomenal precision. The true power of the Roman mission lies in combining all three of these probes. Each method has its own potential pitfalls and uncertainties, but by using them together, they cross-check and reinforce one another, eliminating errors and building an ironclad case. This triple-threat approach will allow scientists to measure the equation of state parameter W with a precision never before imagined. Is it locked firmly at -1, pointing to Einstein's simple cosmological constant? Or does it waver, hinting at a dynamic and evolving quintessence field with the potential for a far more dramatic future? The data from this single telescope could determine whether our universe is destined for a quiet, endless expansion or a more violent end. This is more than astronomy. It is a direct inquiry into the fundamental laws that govern reality, a mission to read the final chapters of the universe by first deciphering its hidden architecture. Light itself is bent by the weight of the cosmos. When a beam of starlight travels across the universe, it does not always travel in a straight line. According to Einstein, the fabric of spacetime is warped by mass, and light must follow these curves. A massive object like a galaxy cluster acts as a natural lens, bending and distorting the light from galaxies that lie far behind it. Sometimes this creates spectacular arcs and multiple images of a single, distant galaxy. But more often, the effect is far more subtle, a phenomenon known as weak gravitational lensing. Imagine looking at a field of distant, faint galaxies through a vast, rippled pane of glass. Each galaxy's image is minutely stretched and sheared, its shape very slightly distorted. No single distortion is obvious, but by studying billions of these galaxies, a statistical pattern emerges. This collective warping paints a picture of the invisible scaffolding that shapes the entire universe, dark matter. The dark matter forms a colossal web, and its gravitational pull is what twists the light. This is where the story connects to dark energy. The growth of this cosmic web is a direct reflection of the battle we have been following. Gravity wants to pull more matter into the filaments and clusters, making the web denser over time. Dark energy, with its repulsive push, works against this, suppressing the growth of these large-scale structures. By measuring how the weak lensing signal changes across different cosmic epochs, we are essentially taking a core sample of the universe's history. We can see how effectively dark energy has been putting the brakes on gravity's construction project. This is the goal of a new generation of astronomical observatories. The European Space Agency's Euclid mission and the ground-based Vera-C Rubin Observatory are engineering marvels designed for this single purpose. They will scan huge portions of the sky, measuring the shapes of billions upon billions of galaxies with exquisite precision. They are not looking for one dramatic lensed arc, but for the faint, coherent whisper of distortion across the entire heavens. The data they collect will be used to create maps of dark matter more detailed than any we have ever seen. And since the distribution of dark matter is dictated by the tug of war between gravity and dark energy, these maps will become our most powerful chart of the invisible force that is accelerating our universe. They will measure the strength of dark energy's push across billions of years, offering us a direct look at the engine driving cosmic destiny. A troubling crack has appeared in the foundation of modern cosmology, and it is growing wider with every new, more precise measurement. This is the Hubble Tension, a stubborn disagreement over the universe's current rate of expansion. On one side, we have the pristine snapshot of the infant universe, the cosmic microwave background. By analyzing the subtle patterns in this ancient light, we can extrapolate forward using our best model of cosmic evolution and predict what the expansion rate should be today. This method gives us one very specific number. On the other side, we have the direct measurements from the local, modern universe. We use the cosmic distance ladder with its Cepheid variables and type 1 a supernova to measure how fast galaxies are rushing away from us right now. This method gives us a different, significantly higher number, the two most reliable ways to measure the same fundamental property of our cosmos are yielding incompatible answers. It is as if you calculated how fast a child should be running based on a baby picture, and then went out and timed that child as an adult, only to find they are sprinting much faster than your prediction. The discrepancy is not large, only a few percent, but in the realm of cosmology, where models are exquisitely precise, it is a glaring anomaly that refuses to go away. This is not a case of simple measurement error, as our tools have become more advanced, from the Planck satellite mapping the cosmic microwave background to the Hubble Space Telescope refining the distance ladder. The tension has only solidified. The numbers stubbornly refuse to converge. This forces a profound question upon us. Is our standard model of the universe, the lambda-CDM model, subtly wrong? For decades, this model, which includes a cosmological constant for dark energy and cold dark matter, has been spectacularly successful, passing every major test. But the Hubble tension suggests a flaw. Perhaps dark energy is not the simple, constant force of Einstein's lambda. Maybe it is a dynamic quintessence field whose strength has changed over time, subtly altering the expansion history in a way that breaks our predictions. Or perhaps dark matter has properties we do not yet understand. Some theorists even suggest the need for entirely new particles or forces that operated only in the universe's early moments. This persistent tension is more than a technical problem for astronomers. It is a potential window into a deeper layer of physics, a clue that the hidden architecture of our cosmos has a design we have not yet perceived. Resolving this puzzle is now one of the most urgent quests in science, for the answer could redefine our understanding of everything, from the first moment of time to the final fate of all we see. These digital universes are our only laboratories for a cosmos we cannot touch. To understand the battle between dark energy and gravity, we must build our own virtual realities, immense computer simulations that play out cosmic history from the first whisper to the final fate. The process begins with a single, ancient snapshot, the pristine pattern of the cosmic microwave background. This fossilized light from the infant universe provides the initial blueprint, the subtle ripples of density that were the seeds of all future structure. Cosmologists feed this blueprint into a supercomputer, programming it with the known laws of physics, particularly the relentless pull of gravity. Then, they set the simulation in motion, tracking billions, even trillions, of individual particles of dark matter as they evolve over billions of virtual years. This is an n-body simulation, a breathtaking digital dance where each particle feels the gravitational tug of every other particle, slowly weaving the cosmic web of filaments and voids. We can watch it form in fast forward, a silent, majestic construction project unfolding on a screen. But the real power of these simulations lies in their ability to test the unknown. Scientists can run the same cosmic experiment again and again, each time changing a single variable, the nature of dark energy itself. In one run, they program in a simple cosmological constant, a steady, unchanging force. They watch as the virtual universe expands, its large-scale structure growing at a predictable rate before dark energy begins to suppress further growth. Then they reset the simulation, this time coding in a dynamic quintessence field, a force that might weaken or strengthen over time. The difference is profound. A weakening dark energy might allow gravity to build a denser, more intricate cosmic web. A strengthening one, a phantom energy, might tear that web apart before it can even fully form, leaving a universe that is far more sparse and empty. By running these countless digital experiments, cosmologists generate a library of possible universes, each with its own unique architectural signature. The final, crucial step is to step back into our own reality. They take these virtual predictions and compare them directly to the real maps of the cosmos, the galactic surveys from projects like Sloan and the future Roman telescope. They look for a match. Does the real cosmic web, with its specific cluster sizes and void distributions, look more like the simulation run with a constant lambda, or the one run with a dynamic quintessence? This is how we test the hidden architecture of our existence, not with a single telescope, but by building entire cosmos in a box and seeing which one looks like home. Perhaps the entire framework of our cosmic conflict is built on a fundamental mistake. We have been searching for a hidden force, a mysterious dark energy, to explain the universe's runaway expansion. But what if the answer is not something we need to add to our equations, but something we need to change about them? This radical idea suggests that Einstein's theory of general relativity, the very foundation of modern cosmology, might be incomplete. It works flawlessly from the scale of planets to the orbits of binary stars, but on the vast, diluted scales of the entire cosmos, could gravity itself be playing by different rules? This is the premise of modified gravity theories, a bold attempt to explain the cosmos without any dark energy or dark matter at all. One of the most prominent ideas is known as modified Newtonian dynamics. It was originally proposed to explain why individual galaxies rotate so quickly without flying apart. According to Newton and Einstein, the visible matter in a galaxy's outer regions should be moving too slowly to maintain their orbits, implying the presence of invisible dark matter holding them in. MND offers a different solution. It proposes that gravity does not weaken with the square of the distance in all circumstances. Instead, at extremely low accelerations, like those experienced in the sparse outskirts of a galaxy, gravity gets a subtle second wind, becoming slightly stronger than expected. This extra gravitational kick would make stars orbit faster, perfectly mimicking the effect of a dark matter halo, but without any invisible substance. When theorists attempted to extend this concept from galaxies to the entire universe, they found something astonishing. Some relativistic versions of MND naturally produce a cosmic acceleration, an effect that looks for all the world like dark energy, but is in fact just a new behavior of gravity on the largest scales. Other theories with names like F of R gravity propose more complex modifications. They suggest that the fabric of spacetime possesses a kind of innate flexibility or elasticity that Einstein's original equations do not capture. Over cosmic distances, this elasticity could manifest as an effective repulsion, gently pushing the universe apart. Think of it like this. You have a perfectly good map that works brilliantly for navigating your own city. But if you try to use that same map to plan a flight across an ocean, you discover it is subtly wrong because it fails to account for the Earth's curvature. Modified gravity theories argue that general relativity is our city map. It is incredibly accurate for local space, but when we apply it to the entire curved expanse of the cosmos, its inherent flatness leads us to invent phantom forces like dark energy to explain what is really just a geometric effect we failed to understand. So why has dark energy become the dominant explanation if these alternatives exist? The challenge for any modified gravity theory is immense. It must not only explain the accelerated expansion and galactic rotations, but also pass every other test that general relativity has already aced. It must correctly predict the precise timing of signals from pulsars, the bending of light around massive galaxies, and the behavior of the cosmic microwave background. So far, no single alternative theory has managed to cleanly reconcile all these observations at once. The evidence from colliding galaxy clusters, for instance, shows that their gravity bends light in a way that appears to be caused by a cloud of dark matter separated from the visible galaxies, a phenomenon very difficult for man to explain. This does not make the pursuit futile. On the contrary, it is essential science. Every time a theorist devises a new way to modify gravity, and it is tested against the data, we learn something profound. We are either confirming the stunning reality of the dark universe, or we are inching closer to a revolutionary new understanding of gravity itself. The very existence of these alternatives forces us to confront the bedrock of our knowledge, reminding us that even our most cherished theories are ultimately provisional, waiting for the next great discovery to either solidify their standing or reveal a deeper, stranger truth. The most terrifying possibility hidden within the dark energy equation is a substance known as phantom energy. This is not the gentle, constant push of the cosmological constant. It is a runaway force defined by an equation of state where the value of W slips below -1. This single, subtle mathematical shift creates a feedback loop of cosmic horror. As the universe expands, the energy density of phantom energy does not dilute or remain constant. It actually increases. This growing repulsive force then makes the universe expand even faster, which in turn makes the dark energy stronger still. The acceleration feeds on itself, growing exponentially without any natural limit. The consequence of this unchecked push is an end to reality called the Big Rip. Imagine a cosmic countdown clock, one that ticks down not over infinite eons but in a finite, predictable amount of time. The end would not come all at once, but in a sequence of escalating destruction. First, the largest structures in the universe would be dismantled. The gravitational glue holding entire clusters of galaxies together would be overwhelmed, sending galaxies flying apart into the void. Next, the fabric of individual galaxies would be torn asunder. Our own Milky Way would be ripped apart, its stars scattered into the growing emptiness. As the phantom force intensifies, it would then attack the bonds within our solar system. The sun's gravity would no longer be able to hold the planets in their orbits. Earth would be flung away into the ever-cooling darkness. The final moments would be one of pure, fundamental disintegration. The phantom force would grow so strong that it would exceed the forces that hold matter itself together. Planetary bodies and stars would be shredded. The electromagnetic forces binding atoms would snap. In the last fraction of a second, even atomic nuclei would be torn apart, their protons and neutrons ripped into a spray of elementary particles. Space-time itself, the very stage upon which the universe plays out, would be shredded beyond recognition. While current observations favor a less violent future, the phantom energy concept is a stark reminder of the high stakes in this cosmic conflict. It shows that the hidden architecture of dark energy is not just a theoretical curiosity. The specific nature of this invisible force, defined by a single number, holds the ultimate power to decide whether our universe ends with a slow, cold whisper or a sudden, violent scream. This faint, omnipresent glow is the oldest light in existence, a fossilized photograph from the dawn of time. We call it the cosmic microwave background, and it is the cooled remnant of the universe's first brilliant flash. For 380,000 years after the Big Bang, the cosmos was a seething, opaque fog of plasma, so hot that light particles were constantly scattered, trapped in a chaotic dance with matter. Then, in a pivotal moment of cooling, electrons and protons combined to form the first neutral atoms. The universe suddenly became transparent, and that trapped light was finally set free, streaming across the cosmos. Today, that primordial light has cooled and stretched into a uniform microwave whisper that fills every cubic centimeter of space, a cold signature of our hot beginning. This is not a smooth, featureless wall of light, however. Imprinted upon it are the tiniest of imperfections, a speckled pattern of minute temperature variations, regions that were ever so slightly hotter or colder than average. These hot and cold spots are the cosmic seeds from which everything we know would eventually grow. They are the blueprint for the entire cosmic web. By mapping these fluctuations with exquisite precision, satellites like Planck have taken the universe's baby picture and decoded its fundamental composition. The specific size and distribution of these spots act as a cosmic barcode. The patterns tell us that ordinary matter, the stuff of stars and planets, makes up only about 5% of the universe. Dark matter, the invisible gravitational scaffolding, accounts for roughly 27%. The remaining 68%, the dominant component, is the energy of empty space itself, dark energy. The geometry of the universe is also written in this light. The paths of these ancient photons have traveled across the cosmos for billions of years, and their journeys reveal the overall shape of spacetime. The Planck data shows this geometry to be remarkably flat, like the surface of a perfectly stretched sheet. In a universe with only matter, this flatness would be an unstable, temporary condition, quickly collapsing into a curved, closed shape. The observed flatness can only be maintained if there is a dominant, repulsive component, dark energy, infusing the vacuum and holding the cosmic fabric taut. The cosmic microwave background does not show us dark energy in action, for the acceleration had not yet begun when this light was released. Instead, it provides the pristine starting conditions, the initial state of the cosmic explosion. It tells us precisely how much matter and energy was present at the beginning, and how those ingredients were distributed. When we plug these initial conditions into our models of cosmic evolution, the outcome is inevitable. With the measured amounts of matter and the observed flat geometry, the only way the universe can look the way it does today, with its vast voids and accelerating expansion, is if dark energy emerged to dominate its destiny. This ancient afterglow is therefore the ultimate anchor for our entire story, the foundation upon which our understanding of the hidden architecture is built. The ultimate fate of the cosmos depends entirely on the victor in this silent war. If dark energy remains a perfect, unchanging cosmological constant, our future is one of profound isolation. Billions of years from now, the acceleration will have carried all other galaxies so far away that their light can no longer reach us. The night sky, now filled with a tapestry of stars, will grow steadily darker. One by one, the galaxies beyond our local group will wink out of view, vanishing over the edge of the observable universe. This is the Big Freeze, a slow, cold death where the universe continues to expand, but becomes increasingly empty and dilute. Star formation will eventually cease as all interstellar gas is consumed or flung apart. The last stars will sputter out, leaving behind a cosmos of black holes, cold stellar cinders, and subatomic particles, all drifting endlessly apart in an ever-cooling, eternal darkness. It is a quiet, lonely, but stable end. This future hinges on the equation of state being locked firmly at -1, a steady push that never weakens or strengthens. Yet if dark energy is something more dynamic, a quintessence field that decays over eons, the entire story changes. In this scenario, the repulsive force could gradually diminish, like a spring losing its tension. After trillions of years, gravity, the patient architect, might finally reassert its dominance. The expansion of the universe could slow, halt, and then reverse, initiating a cosmic recollapse known as the Big Crunch. Every galaxy, every star, every particle would be drawn back together in a fiery, cataclysmic reversal of the Big Bang. The universe would end not in ice but in fire. Then there is the most violent possibility of all, the one we have already glimpsed. If dark energy is phantom energy with an equation of state less than -1, the outcome is the Big Rip. This is not a slow fade into cold solitude. It is a sudden, catastrophic demolition of reality itself, where every structure is torn apart in a finite, predictable amount of time. These are not just philosophical speculations, they are the direct, logical consequences of the physical properties we are trying to measure right now. The long-term forecast for all of existence, spanning trillions upon trillions of years, is being written today in the subtle data from our telescopes. The hidden architecture of dark energy is not just a scientific puzzle, it is the blueprint for our ultimate destiny. This fine-tuning of the cosmological constant is so precise it borders on the miraculous, forcing us to confront a deeply controversial question. Why does our universe possess this one specific, oddly small value for dark energy that allows for our existence? One provocative answer comes from the Anthropic principle. This line of reasoning suggests the universe is the way it is because we are here to observe it. If the constants of nature were even slightly different, life as we know it could never have arisen. This is not a scientific theory in the traditional sense, but a philosophical framework that recontextualizes the entire fine-tuning problem. Consider the strength of dark energy. If its repulsive push were significantly stronger, space would have expanded so rapidly after the Big Bang that matter could never have clumped together. No galaxies, no stars, no planets would ever form. The universe would be a cold, dark, and eternally featureless void. Conversely, if the cosmological constant were a large negative value, acting as an intensely attractive force, the universe would have collapsed back on itself in a catastrophic big crunch long before life had a chance to emerge. Our universe seems to occupy a breathtakingly narrow window of possibility, a Goldilocks zone in the space of physical laws where the balance between push and pull is just right for complexity to flourish. How do we explain this incredible luck? The Anthropic principle finds its most compelling, though speculative, answer in the concept of a multiverse. Imagine not one universe but a vast, perhaps infinite, ensemble of universes, each with its own unique, randomly selected set of physical constants. In this cosmic landscape, most universes would be stillborn or barren. Some would collapse instantly, others would fly apart into emptiness. But in a tiny, tiny fraction of these universes, the numbers would line up by pure chance. In those rare islands of viability, the dark energy would be weak enough for gravity to build galaxies and for beings to eventually evolve and look up at the stars, pondering their own existence. We, by necessity, find ourselves in one of those exceptionally rare, life-permitting universes. This idea is philosophically troubling for many scientists because it seems to move the goalposts. Instead of a single, elegant theory that predicts why the cosmological constant must have its observed value, it posits a chaotic multiverse where every value is tried, and we simply inhabit the one that works. It exchanges a fundamental explanation for a statistical one. Yet, in the face of a fine-tuning problem as severe as the cosmological constant problem, this controversial reasoning remains one of the few potential paths forward, forcing us to consider that the hidden architecture of our reality might be far grander and more strange than we ever dared to imagine. The same physics that drives our accelerating universe today may have once operated in overdrive. Billions of years before dark energy began its work, the cosmos experienced an even more dramatic growth spurt known as inflation. For a fleeting fraction of a second after the Big Bang, a mysterious form of repulsive energy took command, inflating the universe from a subatomic speck to a macroscopic size faster than the speed of light. This was not an expansion of matter into space, but a violent stretching of space itself. The mechanism behind this incredible event shares a deep family resemblance with dark energy. Both phenomena are powered by a dominant energy component that possesses a peculiar property, negative pressure. Think of it like this. If you fill a balloon with air, the positive pressure inside pushes outward, expanding the balloon. But in the fabric of space-time, a substance with negative pressure does something counterintuitive. It creates a kind of suction from within, causing space to stretch itself apart. This is the repulsive gravity that drives cosmic acceleration, whether in the universe's first instant or in its present old age. Yet the contrast between these two epochs is as stark as the difference between a lightning bolt and a steady dawn. Inflation was an unimaginably violent and brief explosion, a burst of cosmic energy of incredible strength that lasted only a minuscule fraction of a second. Dark energy, by comparison, is incredibly feeble and patient, a whisper of a force so weak that it took billions of years to overtake gravity, yet it is destined to persist for trillions more. Why did one end so abruptly while the other persists? The leading theory suggests the field that drove inflation, often called the inflaton, was unstable. It operated at a high energy peak, like a marble balanced on the tip of a mountain, and it quickly rolled down into a valley, its repulsive energy dissipating as it settled. Dark energy, if it is indeed a cosmological constant, is like that marble resting at the very bottom of the deepest valley, a state of stable, minimal energy that will never change. This connection opens a tantalizing line of inquiry. Could dark energy be a faint, residual echo of that primordial inflationary field? Perhaps a small fragment of that initial energy never decayed, or maybe a new, similar field has recently awakened. Some unified theories attempt to describe both events with a single, underlying substance, a cosmic fluid that can behave differently across the vast scales of time. Exploring this parallel provides a profound new context for the force shaping our destiny. It suggests that the acceleration we see today is not a singular, bizarre anomaly, but a known class of cosmic behavior, a second act in a play whose script we are only beginning to read. This fundamental elusiveness defines the entire hunt. Dark energy refuses to play by the rules that have guided every other major discovery in physics. We cannot trap it in a particle accelerator, we cannot bottle it in a lab, and we cannot feel its presence in our daily lives. Its signature is written exclusively on the canvas of the entire cosmos, and only over billions of years. Think of the difference between finding a single fingerprint at a crime scene and trying to deduce the criminal's identity from the slow, imperceptible drift of the continents. One requires a magnifying glass, the other a satellite. This is why dark energy is so phenomenally difficult to pin down. Its energy density is almost vanishingly small. On Earth, every cubic meter of space is filled with this repulsive force, yet its strength is equivalent to the mass of just a few hydrogen atoms in that same volume. This is an energy so feeble that it is completely drowned out by every other form of energy around us, from the light of a single candle to the hum of a computer. We are trying to hear a whisper in a hurricane. This is also why we cannot shield ourselves from it or manipulate it. It is not a substance that flows through space, it is a property of space itself. You cannot block the vacuum, you can only observe what its inherent properties do to the universe over colossal distances and timescales. All our evidence is therefore indirect, a series of profound inferences. We are like detectives who cannot see the suspect, but we can see the entire city slowly being pushed apart by his unseen hands. We measure the stretching of light from supernova. We chart the frozen sound waves in the galactic web. We watch the growth of cosmic structures slow to a crawl. Every piece of data is a clue to the identity of this mysterious force, but we never get to see the force itself. This fundamental indirectness is a core part of the mystery, forcing astronomers to become cosmic sleuths, piecing together a universe-sized puzzle where the most important piece is, by its very nature, forever hidden from direct view. Some might dismiss a cosmic force that unfolds over billions of years as irrelevant to our brief human lives. But this quest is far more than an abstract puzzle. It is a profound driver of progress that touches our world in tangible ways. The immense challenge of detecting dark energy has forced us to build better tools, pushing the limits of engineering and computing. To catch the faint whispers of ancient supernova and the subtle warping of light, we needed telescopes with unprecedented sensitivity and cameras of staggering resolution. This demand has directly fueled innovations in optics and detector technology. Furthermore, the sheer volume of data from sky surveys, mapping billions of galaxies, is so colossal that it has spurred revolutionary advances in big data processing and machine learning. The very algorithms developed to find cosmic patterns in the noise are now being applied to challenges in medicine, finance, and climate science. This technological cascade, born from cosmic curiosity, ripples directly back into our daily lives. Beyond the machines, this pursuit stretches the human intellect to its very limits. It forces us to confront the most fundamental questions of existence. Where did the universe come from? Where is it going? What are the ultimate laws of reality? Grappling with these mysteries inspires a new generation of scientists, engineers, and philosophers, fostering a culture of deep inquiry and wonder. Understanding that we live in a cosmos destined for a grand and dramatic fate, whether a freeze or a rip, fundamentally shifts our perspective. It places our human dramas against a backdrop of unimaginable scale and beauty, humbling our conflicts and elevating our collective achievements. The search for dark energy is a testament to our species' insatiable need to look up and ask why. A quest that not only reveals the hidden architecture of the cosmos, but also builds a better, more enlightened future here on Earth. Our universe might be just one page in an infinite cosmic library. This is the profound vision offered by string theory, a framework that attempts to weave together gravity and quantum mechanics into a single, unified tapestry. At its heart, string theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. The specific way these strings vibrate determines the properties of every particle and force we observe, from the quarks in an atom to the photons carrying light. It is a theory of breathtaking elegance, promising to describe all of nature's laws with one mathematical melody. Yet this elegance comes with a staggering implication, a vast and sprawling landscape of possible universes. The vacuum of space in string theory is not a single, unique state. Instead, the theory predicts a colossal number of possible stable configurations, each with its own distinct properties, including a different value for the energy of the vacuum itself, the cosmological constant. In this cosmic landscape, most of the territory is wildly inhospitable. The vast majority of these vacuum states would have a cosmological constant so enormous that space would either curl into a microscopic knot or explode apart instantly. But scattered across this landscape are incredibly rare oases, pockets where the numbers align to produce a universe that is stable, expansive, and capable of fostering life. In this picture, our universe is not fine-tuned by chance or design, but by selection. We simply exist in one of the rare patches where the vacuum energy is small and positive, a gentle push that allows for galaxies to form and life to ponder its own existence. While string theory remains a mathematical frontier without direct experimental proof, it provides a compelling, if speculative, answer to the cosmological constant problem. It transforms a baffling coincidence into a statistical inevitability within a multiverse. The active quest now is to move from this grand vision to a specific calculation. Can theorists derive the precise value of dark energy we observe from the first principles of string theory? Finding that connection would be a monumental step, finally bridging the quantum world of the impossibly small with the cosmic destiny of the impossibly large, revealing the deepest architectural plan of all. No single nation could shoulder this cosmic investigation alone. The search for dark energy has evolved into one of the grandest collaborative projects in the history of science, uniting thousands of researchers across continents in a shared pursuit. These are not solitary astronomers peering through eyepieces, but vast international teams orchestrating monumental sky surveys, projects so immense they generate petabytes of data, enough to fill millions of home computers. Consider the Dark Energy Survey, which utilized a highly sensitive digital camera mounted on a telescope in Chile to meticulously map hundreds of millions of galaxies across 1/8 of the entire sky. Its successor, the Vera C. Rubin Observatory, is poised to begin its legacy survey of space and time. This 10-year endeavor will capture a time-lapse movie of the southern sky, imaging an estimated 20 billion galaxies and cataloging 37 billion stars. Every few nights, it will photograph the entire available sky, creating an unprecedented dynamic portrait of our cosmos. Meanwhile, from the summit of Mauna Kea in Hawaii, the Subaru telescope's prime focus spectrograph is undertaking its own colossal mission. It will not just take pictures, but will measure the redshifts of millions of galaxies, precisely determining their distances to construct the most detailed three-dimensional map of the large-scale structure of the universe ever made. The sheer scale of these projects defies individual effort. They require the combined expertise of astronomers, physicists, computer scientists, and statisticians, all working in concert to design the instruments, process the staggering flows of data, and extract the subtle signals hidden within. This global cooperation is more than a logistical necessity. It is a powerful testament to a fundamental human trait, our shared, insatiable curiosity to understand the universe we inhabit. We are pooling our collective intellect and resources to answer a question that transcends borders, a question about the ultimate fate of everything we see. Our journey through the hidden architecture of dark energy brings us to a final, humbling perspective. We have traced its story from a shocking anomaly in the light of dying stars to a dominant force shaping cosmic destiny. This mysterious component, constituting roughly 68% of everything, is locked in an eternal struggle with gravity, a silent war that will write the final chapter for all of existence. While its true nature remains just out of reach, the relentless quest to understand it has already reshaped our capabilities, driving innovation in technology and data science that echoes far beyond astronomy. This is far more than an abstract puzzle for physicists. It is a fundamental part of our universe's grand narrative, the invisible framework upon which our ultimate fate is being built. The battle between the push and the pull continues unabated, and with powerful new telescopes and surveys on the horizon, we stand at the threshold of potentially revolutionary discoveries. What do you think dark energy truly is? Share your thoughts on this profound cosmic mystery in the comments, and subscribe to join us as we continue this incredible journey of exploration.